Quantum mechanics is, without a doubt, the most successful theory in all of science. It works perfectly. Its predictions are unbelievably accurate. But here's the crazy part. If you ask a physicist what it all means, what it says about what reality actually is, you're going to get a bunch of different answers. We've had the theory for almost a century, but we still can't agree on what kind of universe it's describing. So, here's our game plan for this explainer. First, we're going to tackle the measurement problem. That's the big contradiction at the heart of all this. Then we'll see why the standard explanation, the Copenhagen interpretation, just doesn't quite work. After that, we'll take a tour of some truly bizarre alternative realities physicists have cooked up. We'll find out why each of those ideas has its own issues, and finally, we'll see why we're kind of stuck in a stalemate. Okay, let's dive right in. To really get why physicists have proposed such strange pictures of reality, we first have to understand the core problem, the one that honestly keeps them up at night. This seems like such a simple, almost philosophical question, doesn't it? But for quantum mechanics, it is the question. The theory is brilliant at telling us what happens when we look at something, when we take a measurement, but it gets super weird and even contradictory about what's going on the rest of the time. And this right here is the heart of the whole mess. Quantum mechanics seems to operate on two completely different rules. On the one hand, you have rule number one. A particle, when left alone, is just this smooth wave of all possibilities, evolving perfectly and predictably. But then, wham! The moment you look at it, the moment you measure it, rule number two kicks in. That beautiful wave of possibilities just collapses, instantly and randomly, into one single concrete reality. How can both of these be true? And that, my friends, is the measurement problem. The theory gives us two different processes for how reality works, but never defines what a measurement even is. It doesn't tell us when the universe decides to stop playing by the smooth and predictable rules and switch to the sudden and random ones. It means the theory, as it's usually taught, is incomplete. Now, the standard answer you'll find in most textbooks is something called the Copenhagen interpretation. But here's the thing. The source material for this explainer argues that this standard picture has a deep logical flaw that makes it impossible for it to be the whole story. The paper calls this the P1 and 2 problem, and it's a doozy. Just imagine an observer, let's call her Alice, inside a sealed laboratory running an experiment. From her point of view, she measures a particle, and boom, the wave collapses. Reality has chosen. But now, what about her friend Bob, who's outside the lab? From his perspective, Alice and her entire lab are just one big quantum system that hasn't been measured yet. So for him, the whole thing, Alice included, is still in a fuzzy superposition. They can't both be right. This thought experiment is famously known as Wigner's friend, and it puts you in an impossible bind. You're forced to make a choice. Either the smooth evolution rule doesn't apply to everything, or you have to give up on the idea that the laws of physics are the same for everyone. It's a fundamental contradiction. So because the standard picture is so shaky, physicists had to get really creative. They started proposing these truly radical, mind-bending pictures of reality, all in an attempt to tell a single, consistent story that works for everyone, everywhere. Okay, first up is probably the most famous one, the many worlds view. This idea is as wild as it sounds. It says the wave never collapses at all. Instead, every time a measurement could happen, the entire universe splits. So in our universe, the particle landed here, but in another universe that just branched off, it landed over there. Every possibility is real somewhere. Then we have a completely different picture called Bohmian mechanics. This one tries to make things more, well, normal. It says particles are actually particles. They're always in a specific spot. The catch? They're being guided along by a hidden pilot wave. It's kind of like a tiny invisible surfer riding a wave that tells it where to go. And a third big idea is called objective collapse. This one says, hey, the collapse of the wave is a real physical event. It doesn't need a person or a measurement to trigger it. It just happens on its own, randomly, all the time, all over the universe. We just happen to notice it when we're looking. So there we have it, 3 different, fascinating, realistic pictures of the quantum world. Problem solved, right? Well, not so fast. The whole point of the paper we're drawing from is that when you look really closely, every single one of these solutions creates its own new and possibly fatal set of problems. And this table just lays it all out so clearly. We already know Copenhagen is logically inconsistent, but look at the others. Many worlds can't explain why our world seems definite and not some bizarre mix of all possibilities.
That's the preferred basis problem. Bohmian mechanics, as cool as it is, actually makes some predictions that flat out conflict with experimental results, and objective collapse theories predict tiny distortions in experiments that we have looked for and have never, ever found. It's like a game of whack-a-mole. You solve one problem and another one pops up.
So, if every attempt to create a consistent, realistic picture of the quantum world just creates new problems, where does that leave us? What happens now in the search for what's really going on?
The conclusion from the source material is pretty stark. We're in a stalemate, plain and simple. For almost 100 years, we've debated this, and not a single one of the mainstream interpretations gives us a picture of reality that is both logically consistent and fully agrees with all our experiments.
The paper really puts it bluntly, and this isn't just some abstract philosophical argument. It's a real roadblock. It suggests that our progress on the next big theories, like quantum gravity or understanding the Big Bang, might actually be stuck until we solve this. We might need to figure out what reality is before we can describe it any further.
Which leaves us right here with this one final mind-bending question. We have these amazing equations that act as a perfect map, predicting how the universe works with stunning accuracy. But every time we try to draw a picture of the territory that the map describes, the picture is flawed. Every single one. So if all our maps are wrong, what does the true territory, the actual quantum reality, really look like? As of right now, absolutely nobody knows.